Hello, my name is Jade Liu, and I will be talking about the paper RSA Key Extraction via Low Bandwidth Acoustic Cryptanalysis by Daniel Genkin, A.D. Shamir, and Eran Tromer. A pivotal part of security is keeping sensitive information private to only the intended audience. In particular, to defend against data transmission interception, crypto systems are used. The RSA algorithm is an implementation of a crypto system. This consists of a public key used to encrypt the message and a private key used to decrypt the message. For example, if Alice wants to send a message to Bob, Bob will first send Alice the public key for Alice to encrypt the message, and after Alice sends Bob the encrypted message, Bob will use the private key to decrypt the message without ever sharing the private key. In this case, we are neither nice-looking Alice nor nice-looking Bob, but we're evil-looking Eve. To come up with a public key, Bob needs to secretly pick two large primes, P and Q, and multiply them together to get n. Bob then calculates phi of n, also known as Euler's phi function, that counts the number of positive integers from 1 to n, in which the greatest common divisor between the number and n is 1. In this case, phi of n is equivalent to multiplying p minus 1 and q minus 1. Bob then picks a random integer modulo phi of n to get e. The pair n, e is now published as a public key. Alice takes this public key n, e to encrypt her message m as m to the e modulo n to send Bob. Bob computes the private key d as the inverse of e modulo phi of n. In other words, e times d is congruent to 1 modulo phi of n. Bob decrypts what Alice sent by calculating m to the e to the d modulo n, and voila, Alice has successfully sent a quote-unquote secure message to Bob. In order to attack this data transmission, we need to figure out the private key, d. So we know that d is the inverse of e modulo phi of n, we know e, we know n is equal to p times q, so let's just factor n. Sounds easy. Well, maybe not. In the RSA 155 cracking in 1999, they found that this very large number n had these two very large numbers, p and q prime factors. This process took 4 months, 290 computers of the internet, and 1 supercomputer. So let's resort to side channels. Instead of attacking the secure algorithm, side channel attacks target the physical environment of the implementation of these algorithms. Examples include timing attacks, power monitoring attacks, acoustic attacks, and electromagnetic attacks, all of which extract information through measuring different effects from computation. We'll focus on the acoustic attack. This specific acoustic attack exploits the different vibrations of electrical components such as capacitors and coils in the motherboard during different operations. In particular, using different secret keys for decryption uses different operations and therefore different amounts of power. So the voltage regulator tries to regulate a stable voltage to the CPU, causing electric fluctuations that are transmitted as sound waves. This behavior comes about in the implementation of RSA by NewPG, a popular open-source encryption software. This visualization is a plot of the acoustic power as a function of time and frequency during the decryption of several RSA ciphertexts. Near the yellow arrows are 2 tones that correspond to each NewPG RSA decryption, first exponentiating modulo the secret prime P and then modulo the secret prime Q. Let's hear how this sounds. Now let's try to exploit this. As a part of NewPG's RSA implementation, we have the modular exponentiation routine that calls a multiplication routine within a loop, which also calls a Karatsuba multiplication within a loop, which also calls a basic multiplication routine within a loop. Now this routine also has a loop with an if statement that does a lot of computation if the current bit of b is 1, but does nothing if the bit is 0. This optimization is crucial for this attack, especially since it's so deep within so many loops. If we can craft a ciphertext such that if the secret key's bit is 0, then most of the bits of b are non-zero, and if the secret key's bit is 1, then most of the bits of b are 0, then we would get one instance that would take lots of computation and time, and another that takes much less. we can hear this difference, and this is called leakage self-amplification. This is the result of this acoustic attack to extract the bits of Q. In the left image, we see that the resulting frequency is around 35 kilohertz, and on the right, we see around 38 kilohertz. The lower frequency corresponds to a longer time for computation, so bits of B were mostly non-zeros, and the bit of Q is 0. And the higher frequency corresponds to a shorter time for computation, so the bits of B were 0, meaning the bit of Q is 1. Now let's see how these ciphertexts are chosen to extract each bit of Q. So this is an adaptive chosen ciphertext attack, which means each ciphertext we send to be decrypted is dependent on the previous ciphertext result. We start with knowing that the most significant bit of Q is 1. Ciphertext C is constructed such that the known bits of Q are the same. The next bit, which is the one that we are extracting, is 0, and the following bits are all 1. So at first we'll send ciphertext 1, 0, 1, 1, 1, 1, 1, 1. And we get this result of a frequency around 38 kilohertz, which means that the extracted bit is 1. Now we know Q starts with 1, 1, so we send 1, 1, 0, 1, 1, 1, 1, 1. And we see a frequency of 35 kilohertz, which means that the next bit is 0. And then we see Q has to be 1, 1, 0, so we send in ciphertext 1, 1, 0, 0, 0, 1, 1, 1, 1. And we get a frequency of around 38 kilohertz, which means the next bit is 1. And you get the idea. We continue this until we're done. So how long does this take? The number of measurements will be equal to the key size divided by 2, since we only need to extract Q, divided again by 2, since there's this thing called the Coppersmith lattice reduction that only needs the first half of Q. So, and then we multiply by 2 to account for possible weak signals that would call for a repeat. This means for a 4096-bit RSA key, this would take 2048 measurements, which takes about an hour for a computer, not for a person. It'll take much longer for me. In the actual attack, the attacker sends a ciphertext to the victim's computer via an email client such as Enigmail that automatically decrypts emails for notification purposes and other purposes, and we will record the response. In this attack, a smartphone is used to record the response, but this must be within 30 centimeters away. So imagine you sitting next to your victim in a meeting room where everyone has their laptops out. All you have to do is put your unsuspecting phone on the table and have it record a decryption, and so you're able to extract that key and decrypt any private messages. The researchers were also able to achieve a range of 1 meter with equipment seen on the bottom image and 4 meters with the equipment seen on the top image, which is super great and not so subtle. So how would you defend against this attack? To reduce the signal, you can use acoustic absorbers or soundproof enclosures. You could also mask the signal by using carefully designed acoustic noise generators to match the frequencies emitted during the decryption. However, these physical countermeasures may be expensive and quite inconvenient. I don't know about you, but neither that soundproof box nor that noise generator will fit into my backpack. A more cost-efficient and effective countermeasure is to change the implementation and the algorithm. This can include ciphertext randomization, where the value sent to the modular exponentiation routine is completely random, and randomizing the modulus during each exponentiation, both of which would prevent this attack. The researchers in this study have disclosed this vulnerability and suggested countermeasures with NewPG developers. Diligently, this paper was not posted publicly until after the new version of NewPG was released. Teamwork makes the dream work. Thank you for watching this video, and I hope you guys stay safe out there.